Alright, here we're going to start talking about trigonometry. So trigonometry literally translates to the measurements of triangles. So really the sides and the angles of triangles, but that doesn't begin to encapsulate everything that this can actually be related to. So specifically, we're really going to be dealing with right triangles. At least this year, actually, we're only going to be dealing with right triangles. But in the future, you're going to see how these kind of triangles are related to circles, even though that kind of seems weird. Right triangles and circles don't seem immediately connected, but they really are. You're going to see how trig functions relate to circles, and even beyond that, when you start plotting these things on a coordinate plane. I'm going to draw this. I don't really want you to draw this, just because it's going to take up the space that we need. But when we're talking about a trig function, when we graph it on a coordinate plane, it's going to look like that, which is basically just a wave. But it turns out that things act like that a lot. This kind of pattern behavior where something goes up and then comes back down and then goes back up, that cycle of a behavior shows up all over the place in our physical universe. Circles show up all over the place in our universe, so do triangles. These trig functions have a lot of different purposes. Right now, unfortunately, we only have the time to talk about how they relate to similar right triangles, but in high school you'll learn how they have a bunch of different applications. Hopefully you'll continue math beyond that and see that they have even more applications. But for right now, specifically, we're going to deal with how they relate to similar right triangles. So we're going to consider these two triangles, A, B, C, and D, E, F. And I'm going to tell you that these two angles, C and F, are congruent, which means that we have two similar triangles, because we know they're right triangles. So we know one other angle is congruent between them, so we have angle-angle similarity. And I just want to set up these proportions. These proportions, even though this is just review from the last unit, are actually really important in this unit. This is going to describe the entire unit, really, just with these three ratios. AB over AC is the ratio that we have here. That's going to be the same as DE to DF in the other triangle. Keep in mind that the only thing I've told you so far is that C and F are the same. I have right triangles that have one angle that's in common. Looking at that second one, BC, the other leg, over the hypotenuse. BC over AC is the same as this leg over that hypotenuse. EF over DF. And then the last one is comparing the two legs. AB over BC is the same thing as DE over EF. Once again, all I've said is that you have angle C. We have a right triangle, and we know that we have something that's congruent to that angle C. It doesn't matter how I drew this triangle. All I told you that I just have that same angle here. So I could draw a separate right triangle. Actually, I could draw 1,000 separate right triangles that also have that angle that's congruent to C, and they will also have this same exact ratio. That ratio doesn't change. Right now I'm just writing it as an expression, but this actually equals a number. That number is going to be consistent. Based on angle C, I can calculate that ratio reliably every single time. As long as C remains the same, that ratio remains the same. That's how we're going to use trig functions this year. Trig functions calculate the exact values of those ratios based on an angle. So if I know I have an angle that remains the same, I am telling you that this angle remains the same, I know that those ratios also remain the same. I'm going to describe this a different way. When you first learned about functions, you probably learned about a function machine. You might not have, but you learned about a function. You might have learned about this, where you have an input, it goes through the function machine, and it comes out as some other kind of output. In this case, that input is the angle. So I told you that we have an angle C that remains the same. That's what we throw into the trig function. This does some crazy math. It's not that crazy, but it's just some math happens there, and it calculates an output, and that output is the ratio, which, like I said, it's really just a number. It's the comparison between these two lengths in a triangle. Okay, that was a lot. If you didn't understand that, that's okay. Just the broad point that I want you to understand is that a trig function does some calculation for us. You input an angle, the output is some number relating to sides. All right, we have to really have a consistent vocabulary about how we talk about these sides. So the side of a right triangle opposite the right angle. When I say opposite, I mean directly across that one. That is called the hypotenuse, and it's always the longest side in that right triangle. The leg of the right triangle across from the marked angle. Okay, so each time you're going to be told an angle, here I'm just going to mark one. It really doesn't matter which one I mark. I'm going to talk about angle C as my marked angle. The leg of the right triangle that's across, I could have used the word opposite there again, I just didn't want to use it because that's how we actually talk about this one. This side across, sounds a bad error, across from angle C is called the opposite side. Still using C as my marked angle. The other leg, the one that is actually directly next to that angle, one of the rays that creates that angle, is called the adjacent side. Adjacent just means it's right next to it. So we're going to say that this is the opposite side, this is the hypotenuse, and this is the adjacent side. So if I had said that this was my marked angle, you can keep that, that's fine, you don't have to erase this, but let's say I had said that A was my marked angle. The hypotenuse never changes, that's still this side. It's still the longest side of the right triangle. The opposite one now is across from that. This one becomes the opposite one. This one becomes the adjacent. So it's all related to the angle that's marked there. Whichever one's directly next to it or creates that as one of the rays with the hypotenuse, that's called the adjacent side. The one that's across is called the opposite side. All right, so we're just going to quickly use that vocab to label the hypotenuse, opposite side, and adjacent side in each of these right triangles. Well, the hypotenuse is the easiest one. It's always across from the right angle. So that is that one, directly across from the right angle. The one that's next to, this is my marked angle. The one that's next to it is called the adjacent side. And the one that's across from it is called the opposite side. In triangle FDE, F is my marked angle. This side is adjacent. It's directly next to that angle. It's creating that angle. DE is the opposite side. It's across from the angle. And the longest side, FE, is called the hypotenuse. We need to be consistent about the way we talk about these because we're actually going to relate these sides in these generic triangles that we really know almost nothing about. Alright, on the back side, in trig we're often going to talk about an angle using the Greek letter theta. It's pronounced theta. Basically, with a line through it. That denotes angle. So we have these three trig functions that we're going to learn about here. They're called sine, cosine, and tangent. The ratios of these are just established. This is just really, there's no y to this. This is basically just a calculator saying that we're going to use the sine function to calculate this ratio. The ratio for sine is the opposite side compared to the hypotenuse. So if I say sine of angle A, I'm talking about the side that's opposite. I'm talking about BC divided by AB. BC over AB. The side that's opposite and the hypotenuse. Cosine relates the adjacent side and the hypotenuse. So in this case, that's AC, and again AB. And then tangent relates the two legs. It's opposite over adjacent. So the opposite side, again, the marked angle doesn't change. I'm always thinking about the side that's across from that marked angle is my opposite. That is BC. And then the side that's next to it as my adjacent side, that's side AC. I do want to point out one thing about sine and cosine. Those are always going to be less than 1, which should make sense because the hypotenuse has to be bigger than either of those two sides. So if the number on the bottom, if this side, AB, is bigger than the side on top, that can't be bigger than 1. That ratio is always going to stay less than 1. Actually, it's always going to be between 0 and 1. Tangent can go either way. We don't know which leg is bigger, so that's not always in between 0 and 1. All right, so we're really just setting up these ratios, but now we're going to be using numbers. We're not going to simplify the ratios, although I don't think we could simplify these even if we do set them up. We're talking about angle P as our marked angle, so I'm going to mark that here. Angle P is my marked angle. I want to set up the sine ratio, which is the opposite over the hypotenuse. 4 over 5. My cosine function is relating the adjacent side and the hypotenuse, so that's 3 over 5. You could plug this into the calculator and it would tell you these numbers. If you did the sine of this angle, angle A, 53.2, that's your input. This is called a function. The output would be exactly the ratio that we just found, 4 over 5, or 0.8. But I'm just going to write it as 4 over 5, just to remain consistent with what we already wrote. The function takes that input and changes it into that output. It takes the angle and turns it into a ratio between those two sides. Tangent is the ratio between the opposite and adjacent. So that's relating this side to this side, and that's 4 over 3. Now I'm going to change my marked angle. Instead of P, now I'm changing it to Q. So with Q as my marked angle here, I'm trying to find the sine function, which is the opposite over the hypotenuse. That's 3 over 5. Then for cosine, that's adjacent over hypotenuse. That's 4 over 5. This is not a coincidence. If you use a different function, you're going to use the cosine function with a different angle, 36.8. It actually gives you that exact same ratio, still 4 over 5. Think about the relationship between these two angles. They're always going to add up to 90. This is a right angle. If angle R is a right angle, the other two have to add up to 90. This is always the case. If you use a complement in the other sine, or sorry, the other trig function, it's always going to give you the same ratio here. Last one, we're relating the, sorry, I should just continue with this. Last one, we're relating the opposite side to the adjacent side, so that's 3 over 4. Which again makes sense. The relationship of these two just switches. All right, last example we're doing together. Ashlyn did not finish completing the table. She showed her relationships for angle P, but not for angle Q. So let's look at the table that we just created here. These two just switch. These two just switch. Because we're just changing the sides that we're talking about. When the marked angle changes, the opposite becomes the adjacent becomes the opposite. And when we talk about sine versus cosine, we're also thinking about switching that from opposite to adjacent. Instead of talking about the opposite here, in cosine we talk about the adjacent side. And we just said that they switch when we talk about a different marked angle. So that's why these are switching. So the sine of Q is going to be the cosine of P, or 6 over the square root of 157. The cosine of Q is going to be the same as the sine of P, the other angle in that triangle, or 11 over the square root of 157. And then tangent of Q is going to be the opposite of that relationship, because really this is relating the opposite over the adjacent, and when we change the marked angle, those two switch, so now the opposite is 6 and the adjacent is 11. Right, I know that was a lot. Hopefully it helps you at least start understanding where these trig functions are coming from and what they're relating as far as side lengths.